Hi guys, and today we are going to be talking about sharding and specifically where Ethereum is with it. I hope you enjoy. On a different note, I'm putting together a 10-part series called Kingmaker, which is designed to take you from zero knowledge of blockchains to hero knowledge of blockchains. I'm doing this because I want you to be the blockchain expert in your company. It is really important to me because without champions, both inside the organization and outside, blockchain won't reach its full potential, and I want you to be a significant part in making that happen. If you'd like to see that, then please like and subscribe to this channel and hit that notification bell, and I'll tell you exactly when it's coming. The first video with us should be around a week to 2 weeks time, but I'll let you know if you subscribe and hit the bell. I hope you're excited as I am about it. I think it's really going to make a difference. But without any delay, let's get into Ethereum sharding. So what is the problem? The world has had a data explosion. From monitoring what people do on the internet to capturing millions of individuals' health data on a microsecond basis, we've caused an exponential growth in how much data we capture. The challenge is, how do we interact with that data? The larger the data sets get, the more computationally difficult it is to use that data. The best way to think about it is imagine a warehouse. If it was full of items, it's more difficult to find something than is stored in your wardrobe, perhaps. It's the same problem with blockchains. Now, the more people that use a blockchain, the more they contribute to the creation of data. Every transaction is a new piece of data. Every new participant, their identity is also a new piece of data, and so on. If 10 people buy and sell Bitcoin between themselves, then there is a small set of transactions to record. But if 10 million people buy and transact Bitcoin between themselves, then there is an exponentially larger, much larger set of data. Instead of explaining the relatively complex dynamics of sharding-based blockchain technology straight away, we will do that a little later, but it's probably better to start with the fundamental way sharding works and then build up from there. So imagine this. You need to find a purchase record that Zeth made, and it's all on one database. How do you search that? Well, you have to go into the data and you select data by Zeth. The computer whirs away in the background and searches through all records beginning with A, then B, then C, then D, and so on until you get to Z. Now, imagine that you have 26 databases, one with the records with A on it, one with records with B on it, and so on, including a database with all of the records of Z. Now, if your application knows to go straight to the Z database, then it is a much smaller search space. You're only searching through all the names beginning with Z because you knew where to look in the right database in the first place. And that is all sharding is at the basic level. Keeping data separate and knowing where data is kept so that you go to the right place the first time. Why is sharding on blockchains necessary then? Well, we know why sharding is important in data-heavy systems, but why is sharding necessary specifically in blockchains? In order to answer that question, I need to explain two concepts. First, what limits the network, and second, what limits the speed of a single node on that network. Let's answer the first one first. Basically, a transaction on Ethereum, like the execution of a smart contract, has to be processed by every node connected to Ethereum. Therefore, Ethereum can only go as fast as any single node connected to the blockchain. The second, what limits that single node, well, it's down to computational power of an individual machine. What does that mean? In blockchains, the acceptance of a transaction is a computationally difficult task. Thanks to the consensus mechanism, which signs or validates a transaction as authentic, the amount of computer processing required to do that is quite astonishing. Approving the addition of a new piece of data, a transaction in blockchain terms, takes several more orders of magnitude more than a database does that's stored on your local computer. And this is really because of the complexity of the consensus mechanism. Consensus, as you know, is the algorithm is used to confirm a transaction is legitimate, that it comes from you and that you have enough resources to complete the transaction and then to settle any changes caused by that transaction. A normal database does this too. When multiple transactions are submitted to a database simultaneously from multiple people, the database has a job to do, and that is to choose which order they came in. This is basically a different type of consensus, but it's consensus. In Ethereum, this is the proof of work consensus mechanism. And in databases, this is often called, or we select to use, something called optimistic concurrency control. Optimistic concurrency checks that when a payment is made, no other transaction has altered the data about the user's balance in between the time that the transaction was issued and then completed. If it has, it just refuses the update. With proof of work, it is far more complicated as there is a need to provide security that the transaction is not fraudulent. And it does that by randomizing which computer or miner approves the transaction by giving every computer a difficult computational task. It is so hard that basically you have to rely on luck to get it right. Whoever gets it right first gets to validate the transaction. The whole process uses a ton of resources of the node, and hence the node can't do anything else, and therefore a node is limited and therefore does not scale. Now let's get into the blockchain sharding, and particularly Ethereum. But let's do a little bit of a history of where it's come from first. The current implementation approach wasn't always the way to scale via a sharding style solution. Multiple other approaches were suggested and ultimately discounted, and these include proof of work, hub and spoke chains, shadow chains, and a change to proof of stake with the Casper protocol. And then I suppose an interesting one that Vitalik proposed in 2014 was that of hypercubes. Now, imagine a hub and spoke model where the main Ethereum chain spun, you could spin off another chain connected to it, which would do its own processing, and when it was complete, return results to the main chain. This kind of looks like a wheel with Ethereum at the center. This works, but it suffers from an attack vector where if you have enough hash power on one of the subchains and combine that with a denial of service attack on another subchain, then you have the ability to sign invalid blocks and submit them to the main chain. This solution to this, or the solution to this, was instead of using a 3-dimensional model of hub and spoke, you would create a 12-dimensional model where the hub was at the center of a cube. Now, instead of spoke chains resolving to the main Ethereum hub chain, they could resolve to other chains on the edges of the cube, essentially resolving along the edges until they got to the hub. Now this would provide a defense against a single attack vector, as the legitimate blocks could kind of sidestep to a neighboring chain before going to the main chain for eventual resolution. However, flaws were found in this model too. Realistically, the data takes too long to replicate across the network of substates, and should that data be misprocessed in one of those, then there would be a data corruption problem, which could only be resolved by winding back to a previous state of the chain. How does Ethereum plan to shard then? Ethereum plans to shard in exactly the same way as I described previously, by physically separating where data and searches on that data take place, so they are not encumbered by what is going on with the main Ethereum chain, or in fact the other shards. As always, it is quite a technical process with randos, random beacon layers, heartbeats and so on, but I'll do my best to simplify, but without losing accuracy. Now, shards will be designed to be separated by some method. Either all addresses starting with a similar number, such as all the addresses beginning with 00 at the end, or a shard will deal with only one type of asset, such as a particular type of token, like a CryptoKitty token. Right. With sharding, when you submit a transaction, you do so directly to the appropriate shard. Shards operate exactly like a copy of the Ethereum main chain. However, the new part is the results of the shard state needs to be sent to the main Ethereum chain so that everybody has the same data. This happens by rolling transactions and data from that particular synchronizing shard into a blob, which is nothing more than a dump of information in one object. These blobs are put together like a chain into collations. A collation is then summarized into a smaller data set called a collation header. The collation header uses a Merkle root to enable validation of the data contained in that collation. You then have these notaries, a type of validating node if you like, which approve these collations on a random basis. These collation headers, and they're stored on the main Ethereum chain through a randomized validation process, and then agreed upon by a committee of validating nodes. And at this point, they're included into the main chain. That's a lot of work. So the whole thing is quite a bit clever. However, it does suffer from some notable problems, and this includes that it is much easier to take over the network, which is serious. I need to explain that. Blockchains that are based on proof of work are secure only as long as there are lots of computers or nodes or miners, whatever you like, who validate transactions. With Ethereum and Bitcoin, this is fine. There are thousands of these computers, 25,000 Ethereum and around 7,000 in Bitcoin at the moment. But let's say there are only 100 validating computers. If you could own 51 of those computers, you could spend other people's money, because 51% of computers tell the blockchain that the transaction is okay, but 49 says that it's not. Blockchain basically believes the bigger number. In Ethereum and Bitcoin, this is not a problem because there are tens of thousands of validating computers. And the likelihood of one person owning 51% of all of those computers is very, very low indeed. However, if you shard Ethereum into smaller pieces, and then the number of computers validating the transactions goes down drastically. If you create 100 Ethereum shards, the current proposition, from a single Ethereum, then each shard only has 1% of the validators stopping fraud. So instead of having to own 51% of validating nodes to be able to submit fraudulent transactions, you only now have to have 1% of that, or 0.51% of the validating nodes. A very low number indeed. There are around, as I've said, 25,000 validating computers on Ethereum. So currently you need to only own around 128 computers, which costs around $4,000 each, around $1 million in total to take over the whole thing. Ethereum holds around $47 billion. So for $1 million, you could control $47 billion worth of investment. That's good money. Ethereum obviously can't be left with this vulnerabilities, obviously. So sharding will swap proof of work for proof of stake. Proof of stake works by allowing those with lots of money in Ethereum to validate transactions and not some random or randomized computer. This changes the game from computing power to money power. And the idea here is people put a bet into a pot. The probability of you winning is proportionate to the size of how much your stake is compared to other people's. If you stake $1 million and someone else stakes $1 million, then you have a 50% chance of making a transaction, which you could choose to be fraudulent. So there is, from a practical point of view, however, no limit to the amount an individual can stake. So the cost of actually submitting fraudulent transactions depends on how many people are participating. But considering if you win, you earn money legitimately, I think there will always be lots of people staking money. And so therefore, 1 million isn't going to cover it. It's more likely going to be in the hundreds of millions. So, as you can see, sharding is a real option when it comes to scalability, and it's best to get sharding in place as quickly as possible. At the moment, developers are reporting that all of the main concepts have been agreed on in rough format. Also, there is a roadmap of 6 phases from basic sharding without the Ethereum virtual machine all the way to something called super quadratic sharding, which is essentially shards of shards of shards as the last development on there. That is the ultimate in scalability. From a code point of view, Vitalik has issued a GitHub repository in May 2018, which gives an insight on how it's working, and there is active development currently. Vitalik has announced that it should be 2020 before Sharding is released for the main chain. It's a long way off in blockchain world, but with Plasma and Casper and Raiden and other types of speed improvements coming soon, we should see better scalability, although not the ultimate scalability we will see with Sharding. Anyway, that's it for today, folks. Please like and subscribe, and I'll see you next Tuesday for more blockchain shenanigans. And don't forget my Kingmaker series, which is coming soon. See you later, guys.